This is the first lecture on electricity, and a couple things I hope before we even get into it. One of the things that I want to point out is energy was a concept that we did a few weeks ago before spring break, right? And everything that we've done since then is still about the conservation of energy. The problems that we did with temperature and heat were still conservation of energy, right? The energy that left one material went into a different material, so it still follows the guideline of energy can't be created nor destroyed, only altered in form. So temperature and heat was really based on that concept. We get energy from one thing and we use it to do other things. Electricity is going to fall into that too, even though we don't talk about energy the whole time, right? Everything that we do is still along the lines of conservation of energy. So just want to keep that in mind. There's topics we're not covering, unfortunately, like sound and light. Still the same things, right? The underlying concept behind all of these is conservation of energy. But electricity, what is it? Well, the first thing we have to do is we have to define a charge. And there's plenty of ways to define a charge, and if you look it up, you'll probably find a different one than I'm giving you. But I like this definition because I think it's a very good working definition. Even though we could argue it's not 100% correct, I think it's a very good working definition. And it kind of underlines some of the things that are going on. So I like to define charge as an excess or shortage of electrons. And if I look at this, we have our model of an atom, and it has protons and neutrons in the nucleus of the atom, and then outside it has electrons. Now, the first example I'm showing you is something that doesn't have a charge, or an atom that's without a charge, because it has 1, 2, 3, 3 protons in the nucleus. It has 1, 2, 3 electrons in orbit around the nucleus. So 3 protons, which are positively charged, 3 electrons, which are negatively charged. So it's plus 3 minus 3 works out to be 0. So this is something that has no charge. But if we changed, if we change this atom some and we remove some electrons, well, now I have 1, 2, 3 plus charges, or 3 protons in the middle that have a positive charge, and I have only 1 electron around the outside. So now I'm short 2 electrons. This is something that has a positive charge because it has more protons than electrons, or more positive charges than negative charges, and it has a charge of plus 2. Plus 2 what? Well, we're going to get into that. But this is still something that's positively charged. There is a shortage of electrons. If I look at the same atom and I change the number of electrons again, well, I still have the same number of protons, 3, but now I have 4 electrons, so now this has an excess of electrons, so this has a charge of minus 1, right? There is 3 positively charged protons, there are 4 negatively charged, so plus 3 minus 4 works out to be a negative 1. This is a charge of negative 1, or it has an excess electron. Now, I like to define it like this because in the vast majority of cases, it is electrons that are moving around. And if we think about it, right, with my examples, I kept changing the number of electrons. Well, changing the number of electrons is an easy thing to do. We could add electrons, we can get rid of electrons. These things happen all the time. And if you remember from chemistry class, moving around electrons doesn't really change much except for the charge, right? And so many things do that. Some things share electrons, some things get rid of electrons. Right? And some things can grab electrons, right? So this idea of swapping electrons is extremely common, and it doesn't have a major effect on the atom itself. But adding protons or removing protons, first of all, is extremely hard to do. We can't do that easily. Matter of fact, most elements, we can't do it at all, right? We don't have the ability to do that. And if you remember from chemistry, if we added a proton, we're actually changing the element. Or if we removed a proton, again, we're actually changing the element. The atomic number for an element is based on the number of protons, right? So if I was able to add a proton, that might be a bad thing because I changed the element from one thing to the other. So that's not something that normally happens, right? We can't take a material and change it to another element. So my point is, by defining it as the excess or shortage of electrons, is it's easy to move around electrons, and we commonly move around electrons. And we move around electrons to build up negatively charges or to build up positive charges. Either way, that's what we do. So, what is the actual charge? Well, the charge is measured in what we call coulombs, and I probably should. Let me go ahead and write that word out just so we have it. Insert. No, that's not what I wanted. 1 second. Here we go. Well, there we go. So what is C? C equals coulombs. And coulombs is the last fundamental charge. At the beginning of the year, the first day, we said that there's 4 fundamental charges that can't be broken up into anything else. And that was mass, time and length, and charge. And we didn't use charge until this point, and I'm pretty sure I said, hey, we'll get to this one. But here we are. Now we're at this one. So coulombs is our last fundamental charge. So a proton has a charge of plus 1.6 times 10 to the negative 19 coulombs. It's a very small amount, right? An electron has a charge of negative 1.6 times 10 to the negative 19 coulombs, right? And just the fact that these two things are very different in a lot of ways, they have extremely different masses and they occupy different spaces on an atom. The one thing they have in common is they both have exactly the same charge, and this actually carries out farther, but they both have exactly the same charge. Which, the implications of that, we're not sure exactly what that is or why that is, but the fact that they both are very different in every other way, except they have exactly the same charge but opposite sign, is a hint of what's going on inside the atom as people try and figure it out and look closer and closer at an atom. So a coulomb doesn't break down into other units. A coulomb is its own base unit. It's the last of the 4 base units. Now, we're not going to measure things by the charges of electrons. We're going to measure things by coulombs. So coulombs is a good unit to use because it fits when we talk about electrical circuits, when we talk about a lot of things based on electricity. We're dealing with not tiny amounts of charge. We're not dealing with values to the negative 19 or the negative 16 normally. We're dealing with things that are 1 coulomb or 0.5 coulombs, right? So, but we have to understand that it is electrons that we're moving around. So if we had something and it had a charge of minus 1 coulombs, and minus 1 coulombs, not a crazy amount of charge. You turn on the lights in like the classroom that I teach in normally, right? There's about a coulomb of charge flowing through the light bulbs every second. You start your car in the morning, it's about 5 times that, right? It's about 5 coulombs coming out of the battery every second. If you have a truck, well, then it's even double that, like 10 coulombs. And if it's in the winter time, well, then it's even more than that. So the idea of 1 coulomb or negative 1 coulombs of charge is not an outrageous amount. It's not tiny, but it's certainly not an outrageous amount. But we need to understand when we talk about charges, we're always talking about electrons. If we said something had a charge of minus 1 coulombs, then how many extra electrons? Now, first of all, we wouldn't know how many electrons, right? Because it's an excess or shortage of electrons. So if something had a charge of minus 1, well, how many extra electrons does it have? It has 6.24 times 10 to the 18 extra electrons, right? And along with that, you should kind of understand where that number came from. I didn't get it, but think about it for a little bit at some point and make sure you say, okay, I know how they turned 1.602 times 10 to the negative 19 into 6.24 times 10 to the 18 electrons. So for a charge of negative 1 coulombs, it takes this many electrons, or it takes this many electrons, right? That's how many extra electrons are needed to build up a charge of minus 1 coulombs. Now, this number we don't have to memorize or know, but we just need to understand how big it is. When I say that, the lights in the classroom have a charge of about negative 1 coulombs flowing through it every second. Well, there's no such thing as a coulomb. What that means is there's this many electrons flowing through the light bulbs every single second, right? So even when we start talking about charges in terms of coulombs, you have to understand a coulomb is made up of a ginormous number of electrons, and that's important. So we can build up charge by moving electrons around, by taking in extra electrons or getting rid of electrons. And we can build up areas that are positively charged and areas that are negatively charged by moving around electrons, which brings us to really the phenomenon that makes all of electricity work, right? And that is like charges repel, unlike charges attract. So if I have 2 areas that both have a shortage of electrons, they will push away from each other. They will apply a force that repels each other. A good example is people that have staticky hair on dry days where your hair stands all up. Well, usually that means that every strand of hair has extra electrons in them, right? And all these hairs are trying to get away from each other, and that's static electricity, right? The hair all kind of spreads out as they try and get away from each other. The other thing we know is that unlike charges attract. If something's positively charged and we put it near something that's negatively charged, they will pull each other towards each other. Right? So there's an attraction between unlike charges, one thing positive, one thing negative, and there's a force of repulsion between like charges when both things are positive or both things are negative. Now, why does this happen? We don't really know. This is a lot like gravity, in the sense that we're not sure why there's these forces that act. Right? These are non-contact forces. They push or pull on each other, even though they're not in contact with each other. Again, just like gravity does. But we know they're there, and we could calculate so much about it. If we look closer at it, which we're not really going to, we'll also see that these relationships of forces between charges is not drastically different between the relationship between masses for gravity. Gravity was the attraction between two objects with mass. Electrical forces is the attraction or repulsion between two objects with charge, right? So kind of just saying them, they sound the same. It takes two of them. But then the other thing is, if we look at the equations, the equations for the force of gravity and the forces of electricity are extremely, extremely similar to each other, which kind of gives us a clue that maybe these two things are kind of the same things, just acting in different ways. But we don't know for sure yet. So let's look at something. Let's look at a simple battery. And a simple battery has these two strips of metal, right? This diagram is calling them electrons. There's a negative electrode. There is a positive electrode. So what we have is we have these two different types of metal, and they're put in some chemical. And this is really all we need to know about a battery. But what happens is we have this chemical, and we have this piece of metal inside this chemical. And what happens is there, between the chemical and the water and the metal, there's a fight over electrons. And the chemical pulls electrons off of this metal. So now this piece of metal has a shortage of electrons, which makes it positive. Now the chemical, whatever it is, has all these electrons floating around with it. But then again, on this side, there is a different type of metal, and they start fighting over electrons, but this metal wins. So what happens is the electrons that are floating around in the chemical get pulled onto this metal, right? So the battle for electrons of this metal loses, becomes positively charged. Again, the battle for electrons of this metal wins, so it becomes negatively charged. And that's basically how a battery works, right? There's two different metals in the same liquid, in the same chemical, usually an acid, but not required, or a base. Usually a strong acid or a base, but those aren't necessarily required. There's different combinations for this, right? There's lots of different types of batteries out there. But it sets up an area where we have a positive charge, shortage of electron, and an area that has a negative charge, because it has an excess of electrons. Overall, the battery has the same number of electrons. They didn't make electrons. They just shifted them around due to these chemical reactions. They pulled them off here. They put them on there. So now we have places of like charges. We have this buildup of electrons, and because like charges repel each other, all these electrons really want to get away from each other, but they have nowhere to go. And here we have this shortage of electrons. If we created a path, then we would have a place where electrons can leave. And once they start leaving this metal, well, they want somewhere to go where they're getting pushed off this metal. But if I complete this path, then they're getting pulled onto this one because, again, unlike charges attract. So these electrons are repelled from this, but they're attracted to this. So they are going to travel like I'm showing, really from the left side to the right side. So we have created a path which allows electrons to move around because they're getting pushed and pulled. Once they get onto this metal where the chemical reaction occurs, these electrons get pulled off here due to the chemical reaction. Then they get pulled back onto here and they complete the path, and then they go through this process again. Chemical reaction, then electricity flows, then it happens again and again and again. So this is what a battery does for us, and this is kind of the basics of electricity. We set up a place that has a lot of electrons. We set up a place where there's a shortage of electrons, and then we create a path from one area to the other, and the electrons flow to where there's a shortage, right? And that's kind of the start or the foundation of electricity. Now, just to understand, to create this path, one thing we need is we need a complete path, right? If we just had a wire that went from here to the light bulb, but we didn't have this red wire, we wouldn't really have a flow of electrons. Sure, instantly a couple would jump on here, but we'll talk about the fact that it won't really be much at all, right? But we wouldn't have a flow of electrons. We need a complete path is one thing that we know we need. The other thing we need in this drawing is a poor drawing as far as the light bulb is concerned. we need a place where the electricity enters an object and where the electricity exits an object, right? So there's always a wire going in and there's always a wire going out, which is what this drawing's showing us. It's just not showing us a great path in and out. Realistically, this blue wire should go to the bottom of the light bulb where it's the input to electricity, and then this red wire should be going to these metal screws, which it's kind of touching, which is the output, right? There's always a very distinct place where current enters and a distinct place where current leaves. But that's overall how we create electricity. With that said, we have one key measurement, which is current. Current is the measure of the flow of charges. If we create a path for current flow, if we create a path, then electrons will move, and they'll move from the negative towards the positive, right? And we can measure the flow of that, how many charges are going by per second. Now, we're not going to measure it by electrons per second, even though that's what's moving around, because the numbers will just be huge, right? We'll be back to these gigantic numbers, which are just not fun to work with, and they cause problems. So we don't measure it by electron, we measure it by Coulomb, right? Which is what Coulomb was invented for. First of all, the measure of flow of charges, the units are amperes, where 1 ampere equals 1 Coulomb per second. So if something has a current flow of 1 amp, which is short for amperes, then we could say, okay, 1 Coulomb is flowing by every second. Or we could say this many electrons are flowing by every second. If something has a 2 amp current, well, it's twice this many electrons flowing by per second. So how do we create current flow? Well, we've already said we make a region that's negatively charged, has an excess of electrons. We have a region that's positively charged, has a shortage of electrons, and we make a path from the negative to the positive. Now, creating these areas can be done different ways. A battery uses chemical reactions, like I say, which is a common way. We use batteries all the time, but that's not the most common way. There's other ways to move electrons. Hopefully, we'll get to it this semester. We also move electrons around by creating magnetic fields, and that's kind of the most efficient way, and we don't need any materials to do that, except creating magnetic fields. We need a magnet. So magnets can push electrons around and set up areas of negative charge and positive charge too. There's multiple ways to do it. But next thing I want to talk about is I want to talk about that path. When I say we create a path for electrons to move, we have to do very specific things. We have to have something that allows electrons to move. Air is not a good path, right? If it did, there'd be electricity flowing all over the place, which would be bad. We know other things, rubber and wood, not good paths. We don't create paths out of wood and out of rubber. So electrons can flow if there's a path, and a path is usually a conductor. A conductor is a type of material that allows electrons to flow easily, and conductors are materials with free electrons. So what does that mean? Conductors are materials with free electrons. So this goes back to chemistry, and we're not going to spend a lot of time talking about chemistry, but most people remember this. Back when you learned about chemistry, a lot of bonds had to do with certain atoms wanting a few extra electrons, and other atoms wanted to get rid of electrons. It had to do with their outermost shell. And for all cases, so if we remember from chemistry, sorry about that, if we remember from chemistry, there were certain atoms that on their outer shell, they were short 1 or 2 electrons. And in order to get that outer shell full, it was easier for that atom to go try and find other electrons. So they would try and grab other electrons to fill that outer shell. Usually that shell takes like 8 electrons, if you remember. And if it had like 7 electrons in the outer shell, it needs 1 more to be full. So it tends to go grab another electron from somewhere else. It might share it with another atom. It might take it completely away from another atom. Either way, not a good conductor. On the flip side, there was atoms where the outer shell only had 1 electron in it. So what it tended to do is it tended to get rid of that electron so the shell underneath was full. That's a material that's a good conductor because they tend to have, in order to have the same number of protons as electrons, they would have 1 or 2 electrons in the outer shell, and it didn't really want those electrons because that was an unstable situation for it, so it tended to get rid of those. Those are good conductors. They have what we call free electrons. A free electron is really an electron that's not being held by any one particular atom. This atom has a certain number of protons, a certain number of electrons, but it has 1 electron more than it really wants. So what does it do? It gets rid of it, and that electron floats around, and it might attach to another atom, but now that atom has this electron, one electron in its outer shell, so it tends to get rid of it again, and these electrons kind of just bounce around, and they're never attached to any one atom for long because no atom really wants it. That doesn't make them negatively or positively charged as a whole, because if we looked at like a piece of metal or a conductor, right, all the protons and electrons are all still there. There's just a certain percentage of electrons that are floating around randomly, not attached to any particular atom. So if that makes sense, then that's what conductors are. Conductors conduct electricity because as we push electrons through these conductors, no atom really wants these electrons because they have a full outer shell already. So these electrons are free to move. But not only are the electrons that are leaving the battery free to move, there is a whole bunch of free electrons in the wire that are already bouncing around randomly. And if we give them a path, then they'll start moving in that direction. So for example, right, the electrons, these 4 electrons are free electrons that are already in the wire before we do anything. So if we all of a sudden connect this side to negative, this side to positive, the electrons that are in the wire will start moving towards the positive and away from the negative. So it's not just electrons leaving. There's electrons in the conductors themselves that are already ready to move in whatever direction you give them a push. Which brings 2 major parts of electricity, which is current is always uniform and instantaneous. If I create a path for electricity, the instant I create a path, there is already current flowing everywhere in that path. Right? For example, here we go. I have this diagram of a circuit that I made. Here are batteries. Now, the gold side of the battery is the positive. There's a shortage of electrons, and the black side is negative. That's where there's an excess of electrons. We've all seen a battery before, I think, right? So we expect electrons to come out the negative and go into the positive. Now, I'm going to start this in a second, and right now we don't have a path because right over here the circuit's broke. So I don't have a path for charges to move around. Sure, they can get to here, but they're not going to get there because there's already electrons in the wire too. So there's really nowhere for the electrons to go if they wanted to leave the batteries because there's all these free electrons in their path. So with that said though, when I close this switch, there we go, when I close this switch, current flows everywhere instantly, right? That doesn't mean the electrons here instantly appear other places, but there's a whole circuit or there's a whole path created and there's electrons ready to move everywhere in that path. So as soon as I create a full path, a complete path, current flows everywhere, right? So to give an analogy, it's not like turning on a hose and waiting for the water to travel out of the faucet to get to the end of the hose. It's not that at all. It's as if the hose is already open and it's already full of water ready to flow, and then you open the nozzle at the end and then water shoots out instantly, right? Water starts moving everywhere. It's the same type of thing here. If we create a path with conductors, then current flow is instantaneous, right? It starts and it flows everywhere at the same time. Now, the other thing is that current flow is uniform. So let's see what I mean by that. Again, we make a path, current is instantaneous. With that in mind, if we look at this, I'm actually going to back up to this other picture. If we look at this, we have all these free electrons flowing through a piece of wire. But the thing is, these 2 electrons can't move to the right until these get out of the way. And these can't move until these get out of the way. And these can't move until these get out of the way. Because sure, there's a bunch of negative charges here pushing these electrons, but there's electrons in front of it that are pushing back on it, right? Because all of these electrons, all these electrons are repelling each other. So in order for all these electrons to move, these electrons have to move out of the way. So we could kind of imagine, I kind of envision them as marching or something like that. When these move to the right, everything behind it moves with it, which is also what we mean when we say that current is always uniform, right? All the charges move together. They move instantly, they all start at the same time, and they all move together, right? They don't like some go real fast out of, some go real slow. They all move as a unit. And these 2 concepts, current is uniform and instantaneous, are probably the most important parts of current that you need to understand. There's a lot of misconceptions about it, and people don't understand how this works. these two concepts really drive all the math behind electricity, or at least the current flow of electricity, uniform and instantaneous. So if I go back to this circuit that we had, it's going to start at the beginning, but again, we could see first that current is instantaneous. When I create a path, current flows. When I break that path, current stops, and it stops everywhere, right? Which is what a light switch does in your house, right? You create a path when you close it, you break the path when you open it, current flow instantly starts, instantly stops. But now let's look at something else. When I say current is uniform, well then what do I mean? Well, if we look at this, there is 6.75 amps coming out of the battery. We're not going to figure out how many electrons that is, right? But there's 6.75 amps coming out of the battery. And we could see that the electrons come out. Some go this way, and some go this way. But again, they all kind of march together. So what does that mean? If there's 6.75 amps coming out of the battery and in this wire, well, there must be 6.75 amps going into the battery. And that makes sense because current is uniform. If there's that many electrons coming out, there's got to be the same amount going in, right? That's part of what we mean by current is uniform. If there was more coming out than going in, then that means somewhere in this path we were losing electrons. They were dying or disappearing or something that's simply impossible, right? We can't breed electrons. We can't get rid of electrons. They're there. So whatever's coming out has to be going in on the other side, right? That's part of being uniform. Those two numbers have to be the same. So 6.75 and 6.75 got to be it. But also, if there's 6.75 coming out of the battery and there's 2.7 going this way, well, 6.75 coulombs are coming out, 2.7 are going this way, well then it's got to be 4.05 are going this way because this and this have to add up to the 6.75, right? So 4.05, 2.7, 6.75. Now, let's go to this next one. There's 4.05 amps here. There's 2.7 here. There's 1.35 here. Again, we know how much current's here. It has to break up, and whatever's flowing here and here have to equal what that is. We go over here, 1.35, 2.7, 2.7. All three of those have to add up to the total current. Right? If we take those numbers, well, they got to add up to the total current of 6.75, right? Which is a major concept and goes along with this idea that current is uniform. This plus this plus this have to equal this. This breaks up into this and this. This breaks up into this and this, right? That's part of what current is uniform means. Now, before we go any farther, this is an okay drawing, right? Because it's trying to show real things, real light bulbs, real wires, real batteries. But we're not going to try and draw that stuff. We're going to draw schematic symbols, which makes the drawing a lot easier, especially when we're drawing things by hand. So here are some of our symbols. Our symbol for a wire is simply a straight line, which is great, makes it nice and easy. A battery is a pair of lines where one is long and one is short. Now that's kind of a significant one because it means some stuff that it doesn't show us. First of all, if we see a pair of lines, one short, one long, we know we're talking about a battery. The other thing we know is that the long side is always the positive side of the battery. The short side is the negative side of the battery. So the short side is where electrons leave. The positive is the long side where electrons enter, right? So just by looking at it, I know which part of the battery is which. Negative side, positive side. Now, it's not always one pair of lines. Sometimes it could be multiple pairs of lines, right? This is also a battery. And if I wanted to, this is also a battery. So as long as it ends, one side's got a long end, the other one's got a short end, it's still considered a battery, right? We'll never see a battery drawn like this. That simply won't work, right? Because that implies that both sides of the battery are negative. So that's not possible, right? And we'll certainly never see one that goes like this. Because again, that would imply both sides of the battery are positively charged shortage of electrons. And that's not possible, right? So we could see anything like this. I tend to draw this because it just makes it easier to notice, hey, I'm talking about a battery. Where sometimes when I just draw two pairs of lines, it can get confused with something else that we haven't talked about, like a capacitor or or some other electronic component. So I tend to draw this because it's just more obvious that I'm talking about a battery. But why can there be multiple pairs of lines? Which is actually a point we don't have to worry about too much in what we're doing, but in the real world it's kind of important to understand. Every pair of line represents a cell. So if I go back to this drawing, I have 1, 2, 3 batteries in the circuit. So if I was looking at the schematic symbol, it would look like this one. 1, 2, 3 pairs of lines means 3 batteries. So the pairs of lines usually represents how many individual batteries you have or how many cells in a big battery. Right? Your car has one battery, but it actually is made up of multiple cells in there. So that's what the pairs mean. But either way, a short and a long, that's how the pairs work. A light bulb is this, or a light bulb could also be, which is not drastically different when you freehand draw it. You could also draw it like this, and then put a circle around it. And a resistor, which we're going to talk about in a little bit, but important to know, a resistor is a series of jagged lines, right? And then a switch looks like this. Right now the switch is open. If I move this line down, the switch would be closed. I would now have a path for current flow. So these are the schematic symbols that we're going to need to know. If you need to write them down at some point, you should write them down, but you're going to get used to them real fast because we're going to be drawing a lot of circuits. And we're not drawing the circuits like this. We're going to be drawing the circuits like this because it's faster and it's easier for everyone else to read. Which brings us to our one big law for electricity. Now, this isn't drastically different than what we've already said. We said that current is uniform and instantaneous. Well, this law is saying the exact same thing. It's just saying it a different way. If current is uniform and instantaneous, then that means is the current flowing into a junction must equal the current flowing out. This is what we know as Kirchhoff's current law. And again, it's not saying anything different. It's just saying it in a way that we could write equations. So let's look at this circuit. Now this circuit's using resistors, and again, we haven't really talked about resistors, I get that, but we have this path. We have electrons flowing out here. I have two paths. Some of the electrons go through resistor 4, some electrons go through 1, right? The ones that go through 1 go through 2. The ones that go through 4 split. They go through 3, they go through 5, then they recombine. So if I drew some arrows, right, the current is flowing this way, or the electrons, let me just say the electrons are flowing this way, and this way. We're going to change kind of the direction current flows later. But we could see that the electrons are coming out this side of the battery. They're going this way. They're going this way. They're going up through here. They're going this way. Or after they go through 4, they could go down through here. And they go this way. And then out of 2, 3, and 5, they all combine. And they go down through resistor 6 back to the other side of the battery. So when we understand they're leaving one side of the battery and going into the other side of the battery, we can start seeing the paths that they could take, right? And none of them are going to reverse. None of them are going to get to here and say, oh, maybe I'll go back this way. No, because they're getting pushed away from this side. They're getting pulled towards this side, right? So they have these set paths that they're going to take that automatically start to happen because of the way they're getting pushed and pulled. But that's not the law. The law says the current flowing into a junction must equal the current flowing out. So we're going to make a whole bunch of situations here, and I've pre-marked some of the junctions. Now, what's a junction? A junction kind of is anywhere we want to pick. It's a place where wires connect. And we could argue on this circuit, well, anywhere I want. I could say, oh, well, this is a junction as far as I'm concerned, and that works. Some places aren't great to pick, but they're still right? You can't find a place and say, oh, this law doesn't work here. It's just that this law is very helpful in certain places. In other places, I wouldn't say it's so helpful, and it might actually make things confusing. So we have to kind of pick our junctions, which takes a little practice, but most people catch on kind of fast. So let's say that I picked right here A, and I said, all right, this is my first junction. I'm going to call it junction A. So I know the current is flowing this way. So the current that's flowing into this point right here is coming from resistor 6. Now, before I do anything else, let me back way up because I didn't do it. But let's go all the way back to my definition of current. There it is, and at some point we need to write it. Current is represented by the letter I. Current is represented by the letter I. And why is it I?
No, I'm not saying it's nice.
Now, why is it I? I'm not 100% sure why they picked I, but I do know that in Latin, the word for current begins with I, so they used the Latin word and got the symbol of I for that. I think C's just been used by a few other things, so C is kind of already taken. So I is a symbol for current, and now this is an important place to know that because we're going to be using the letter I. So, sorry, back to junction A. The current flowing into the junction must equal the current flowing out. So when I look at the circuit, the current flowing into A is coming from resistor 6. So I can say the current of 6, that's the current in, and that's got to equal the current flowing out. Now notice, I don't care about anything before 6. Once I pick the junction, I care about what's immediately before, I care about what's immediately after. So the current flowing in is coming from resistor 6. The current flowing out is going to the battery. So the current of resistor 6 is equal to the current of the battery. Now that's important because that's telling us that all the electrons that leave the battery all go through resistor 6 at some point, right? They travel through the circuit. They could take different paths to get to 6, but everything that comes out of the battery goes through resistor 6. So I could also say that the current coming out of the battery and the current through resistor 6 is also the total current, right? Everything that comes out of the battery goes through resistor 6, or everything that flows through resistor 6 goes into the battery, right? So I can make these statements. Now, that's a great junction to make. It makes one thing very clear. All the current goes through 6. If I pick another place, like B, I could say something else. Well, first of all, I could say that the current flowing into this junction, well, the current flowing into B all comes from the battery. So I could say the battery, the current of the battery, I'm just going to make it a B this time. That's the current flowing in. Well, when it flows out, where does it go? Well, here in this junction, it splits. Some goes this way, some goes this way. And again, I don't care about all this stuff over here. I care what it's immediately before, what's immediately after. So the current coming out of the battery equals the current through 4 plus the current through 1. Because if I look at B, the current flowing in comes from the battery, and the current flowing out goes to either 4 or 1. Some of the charges come out, they go this way. Some of the charges come out, and they go this way. Now I'm going to go back to I'm going to go back to this after. It's not the exact same circuit, but we'll run it again just so we could see that the current split, the charges split, and they take different paths to get from one side to the other if we didn't fully notice that. But let's pick another junction. Let's pick junction C right here. If I pick C, the current flowing into C is coming from 4. That's got to equal the current out. Well, when the current goes out of C, it could either go to 3 or 5. Now, each equation I'm making is its own equation. Nothing saying like 6 and 4 are equal or anything like that, right? These are relationships based on these junctions. We're going to see as we get into electricity, we have to keep track of these rules and figure out what they apply to, right? The current law has to do with current and current only. But we can make all of these equations, and I can make a few more. If I look at D, the current flowing into D came from resistor 1. Current flowing out of D, well, where did it go? Well, all of it that came out of 1 immediately went to 2. So the current of 1 equals the current of 2. And that makes sense. Every electron that goes through resistor 1 ends up all going through resistor 2 because they're part of the same path. And the last one I picked was E, which is probably the last important one. The current flowing in equals the current flowing out. So if I pick E, where does the electrons come from? Well, they come from resistor 2. That's true. But they don't just come from 2. Some electrons are coming from 3. And some electrons are coming this way through 5. So the current flowing in is coming from multiple places. It's coming from resistor 2, resistor 3, and a resistor 5. And again, I just care about what's immediately before and immediately after. So I don't care about 1 and 4. They don't show up in this equation. Sure, before they went through 2, 3, and 5, they came from somewhere, but I don't care about that. I care about immediately before. So what flowed into E? Current from 2, current from 3, current from 5, and it all combined and flowed out, and then where did it go next? Well, all of that equals the current through 6. So for this circuit, I can make all of these equations for current, and every single one of them mathematically has to be true. So we showed this with these numbers, but let's turn this on again. Okay. Maybe. Oh, I know what I gotta do. I gotta get off draw. I don't know if I could show you this. There we go. So that took a little while. So to finish this lecture up, we see current is instantaneous. We create the path, we break the path current flows, and then as we follow electrons, every electron that gets here, some go this way, some go this way. As we follow these electrons that get to here, some go this way, some go this way. Electrons from here, here, and here all combine to go back into the battery. So this circuit isn't drastically different than the one I drew, but there's tons of circuits out there, right? But then again, what we're looking at here really is Kirchhoff's law. 6.75 amps is flowing this way. 2.7 and 4.05 add up to 6.75. The current flowing into this junction equals the current going this way and this way. And the current flowing into this junction, well, this is the current flowing in, has to equal this plus this, right? 2.7 plus 1.35 equals 4.05, right? So these add up. And then this one plus this one plus this one have to equal this one, because if I pick like this junction, the current flowing from here, and from here, all combine to give us this one. So there is Kirchhoff's current law. All right, so that's current. Wouldn't be a bad idea to look at some other sources if this lecture doesn't make full sense to you, because we're going to look at current flow, but we're not going to look at current flow by itself. We're going to have to combine current flow with other measurements to make this work. But this is a long video, so I'm going to stop there.